just dead weight. Extra baggage. Please look up. If you have extra neutrons, it's called a heavy isotope. If you have less neutrons, it's called a light isotope. Yes? Less than the average. The atomic mass number is the average weight of that element. Some are heavy, some are light. If it's less than average, it's called a light isotope. If it's more than average, it's called a heavy isotope. Check this out. This will make a really big difference when we talk about nuclear energy. Here's a really important fact about neutrons. If you look up high, like at helium, helium's atomic number is 2. So how many protons does it have? 2. And the atomic mass is, so if it has 2 protons and it weighs 4, how many neutrons does it have? Right? 2 protons, 2 neutrons makes 4. Right? This makes a big difference later, so watch this. Small atoms cannot hold a lot of extra neutrons. Like on a scooter, you can't carry somebody else's baggage, right? Because you're on a scooter. As you start to get bigger, like germanium, germanium has 32 protons and 40 neutrons. That's got a few extra. Because, you know, if you have like a Volkswagen Bug, you can carry somebody else's bags, 1 or 2 extra, no big deal, right? And when you get to the really big stuff, like radon, it has 86 protons and about 136 neutrons. A lot of extra baggage. Because, you know, like a school bus, you can strap all kinds of luggage to the roof, no big deal. School bus can carry plenty of extra weight. Remember this fact. It'll make a big difference later. Small atoms cannot hold a lot of extra neutrons. You should write that down. But big atoms can hold many, many, many more neutrons than protons. In other words, the ratio of proton to neutron is about 1 to 1 at the top, 1 to 1.1 a little lower, 1 to 1.3 a little lower. By the time you get to the bottom, the ratio is 1 to 1.5 or more. Now, I see a lot of you just giving up already, like, well, I'm not going to write that down, so I don't know what he's talking about. But you have to write these things down. And if you don't have questions, you'll have to ask me about it, because we're going to build on this. So you have to be active. Don't let this go. Don't give up. Yeah? That's about right, yeah. Yeah. So the ratio of proton to neutron up at the top is 1 to 1. Every proton gets 1 neutron, and that's it. When you're at the bottom, if you have like 50 protons, that one has almost 70 neutrons.
What about hydrogen? Not less.
Hydrogen is the one exception. It's the only one that doesn't have neutrons.
There's no neutrons?
No neutrons. 1 proton, 1 electron. Kind of weird. But it's just hydrogen. That's the ratio of 1 to 0. So now look. Remember, those different versions with variable numbers of neutrons, we call those isotopes. Variable number of electrons, those are ions. Variable number of neutrons, they're called isotopes. You have to know that word. It comes up a lot. Heavy has extra baggage, bonus neutrons. Lighter has fewer neutrons. The atomic mass is the average protons plus neutrons plus electrons. Please look up. The average uranium has 92 protons, 146 neutrons. There's your ratio of 1 to 1.5. So when you add those up, that's 238. That's the weight, the atomic mass of uranium.
Variable electrons,
Ions. Here's a fun fact about uranium. When you find it on Earth, like in a rock, almost all of uranium ore is the average type, 238. A few facts you should write down about 238. It's highly stable, meaning it's barely radioactive. Average uranium, it is radioactive, but not extremely. It's very common. Almost all of it on Earth is average, is the 238. Very common, fairly stable. People use it to make very heavy ammunition for war. So there's these types of bombs called bunker busters that break underground caves because they're so dense and heavy. Those are made of uranium. They're just really heavy uranium. Because, if this thing was made out of uranium, it would weigh about 15 times what this thing weighs. Super heavy. Heavier than anything else. It's the heaviest thing on Earth. But in nature, there is a very rare isotope that we use for nuclear reactors. Please look up. It's called uranium-235. It's very rare in nature. Less than 1% of all the uranium is 235. That's what we call the radioactive fuel. It's fuel grade. Yes?
So we mine uranium-238 and enrich it to make it usable for reactors? Or we use 235 for reactors?
We mine uranium ore, which is a mix, mostly 238, but a little 235.
Okay.
And then we shave off the stuff we don't want, so this becomes more common. That's enrichment. Look, if I wanted to enrich for brown kids, I would kick out all the white kids, and the brown kids would appear more common. Does that make sense? If I wanted to enrich for white kids, I would kick out all the brown kids, and that would make the white kids look more common, right? If you want to enrich, you keep the stuff that you want, and you get rid of the stuff that you don't. So please look up. You take the normal uranium ore that comes out of the ground, you grind it up, you spin it around, and all the heavy stuff falls to the bottom. Then you shave that off, and that's what enrichment is. Getting rid of the more common, so you've got relatively more of the fuel. The process of enrichment is shaving off a bunch of this crap so that this looks more common. That's what enrichment is. Iran is in trouble because they don't have global permission to do this process. They're getting rid of the crappy uranium and keeping higher percentages of the good stuff. Are there any questions about this? Yes?
How do you get rid of the common uranium?
You grind it up into a powder, and you put it in a suspension, and you use a centrifuge to spin it. And when you spin things in a suspension, the heavier things go further down because they're heavier, so they're more flung by the centripetal force, and the light stuff tends to float toward the top. So you take that plug of uranium shavings, you cut off the bottom, then you grind it up again, you mix it in water, and you spin it again, and you repeat that like thousands of times. Yes?
Why are they in trouble for doing that?
Because if you enrich it to 3% of this stuff, you can use that to run a nuclear reactor, and we'll do that next. But if you enrich it to about 20%, you can start to make dirty nuclear bombs. And if you enrich it to 70 or 80%, you can make really, really hot explosive nuclear bombs.
Is uranium, there's a bad stuff that they don't want, can that be used for anything else, or does it just get wasted?
You can make like heavy ammunition out of it. You can make like pots out of it. It's just a really heavy metal. It's slightly radioactive, so you would not want to make pots out of it, but it's just a really heavy metal. And usually, nobody worries what any country's doing with this crap. Because, we have that in Carpinteria. Like, you can dig it out of the ground and carve. It's not that special. Many countries are sitting on huge uranium reserves. It's not a big deal. The technology to do that shaving off the heavy stuff, that's actually kind of complicated. That's the scary part. If they get good at it, then they can make weapons. Yeah?
So it starts at 99.28.
Yeah.
And then they cut it down 70.72%. And then it's enriched?
No.
No? I'm just curious if like the difference between the copper and the bottom there.
No problem.
The enriched.
Those add up to 100%. Because all the uranium on Earth is mostly this kind and a little bit that kind. But this stuff is useless for a nuclear reactor. You can't do anything with it. This stuff is good for a nuclear reactor. That's what you're looking for. This is what we need for a nuclear reactor. So you just start getting rid of this, and in comparison, this becomes more common. So when you can shift the ratio to 97 to 3, that's called enriched. That's fuel grade.
So then the 97% is the...
Still the crappy stuff that you don't need. 97% is still the unwanted type. That's no good. We still don't need it. But 3% is enough that you can make fuel out of it.
But they still use that 97%.
The 97% is just crap in the way, but when you get the 235 up to 3%, then that density of 235 is good enough for nuclear fuel.
Still there, it's just not used.
That's right. It's just other crap in the way. That's right. Yeah. What else?
What does slightly radioactive mean?
Radioactive means that pieces fall off. Slightly radioactive is that they rarely fall off. Highly radioactive is it's always emitting stuff really fast.
So what's the half-life of 238?
Look it up on your iPhone. I think it's 1.8 billion years.
Oh, so it's really long.
Right. Probably 1.8 billion, but look it up. Look it up. I'd be really curious. Anybody else? Yeah.
What does radioactive actually entail?
But I just told him that it gives off extra parts.
So meaning like it decays, so like you wouldn't want to use that as a pot because like you would swallow stuff.
Yeah, that extra neutron might travel through the food into your body and then be bouncing around, and if it tweaks chemical bonds in your DNA, then that DNA could cause cancer
So it's a
or
misconception.
superpowers.
So it's a misconception that by standing next to it, or could it be in the air?
Radioactivity is little subatomic particles moving through the air,
Okay.
or enough energy to cause them to break up in you. And that's everywhere around you. Standing next to it, you're more likely to get it.
So it's easy to not be affected by radioactiveness if you have protective stuff.
It's very difficult to block radioactive stuff. You can't really protect yourself from it very easily. The odds of radioactivity having a bad problem in you are pretty close to zero, because almost every chemical bond in your body doesn't matter. If you kill a skin cell, who cares? If the outside of a skin cell has a chemical change, who cares? The problem is, if the radioactivity causes a change in one of the very special bonds that manages cell growth, like DNA or the proteins that regulate cell growth, because then you can end up with cells growing like crazy, and that's the whole cancer, tumor, other problems later. The odds of that are extremely small. Almost all the radioactivity that touches you is irrelevant to you. By raising the radioactivity, you raise the chances of the rare outcome. So cancer becomes more likely when you have more radioactive exposure. Got it?
Mm-hmm.
Other questions for me? I like when you ask questions, but I got to move on.
4.46 billion years.
Thank you. Look at my map, my chart. Black is solid, blue is liquid, green is gas, and what is gray?
Synthetic.
Synthetic, make-believe, doesn't exist on Earth. Look at uranium. It is the heaviest you can make something before you get to the make-believe stuff. These are all make-believe. The only reason that people make them is so they can name it and get famous. That's it. All of these are like token elements. They have some value to science, but pretty much, really, honestly, nothing. They don't exist on Earth, so nobody's ever used these for anything. They don't actually do anything.
Why are there just
They're just an extra large atom. It's like, hey, look, I was able to make it. But who cares, because it's going to fall apart. It's like, you can only make a house of cards so tall. And it's like, hey, look, I made a bigger... Oh, that's pretty cool that you made a bigger one, but it doesn't really count for anything because you can't do anything with it. All of these synthetic, they're just make-believe to prove it's possible. So theoretically, they could exist in the universe. And they probably do exist in the universe. But on our planet, with our heat and our pressures, they're irrelevant. They're synthetic. They're man-made. Except for uranium. Uranium is the biggest thing. It's right on that edge. It's stable enough to exist on our planet, but it's right at that Goldilocks point where it's just barely stable enough to exist on our planet. Everybody understand what I'm saying?
Is it so heavy?
Yeah, exactly. It's got so many parts. It's like a bus with like a refrigerator on top and a stove on top and your mom on top, and it's like all this extra baggage. And it's just barely holding it together. It's just barely holding it together. Somebody's like, hey, can I get on board? And that's a problem because it might fall apart.
Is that because it has so many neutrons?
Yes. And so many protons, by the way. It's the most protons that you can hold together. 93 doesn't work. It's too many. So watch this fun fact. Uranium-238, relatively stable. We use it for ammunition. It's called depleted uranium ammunition. So you can make bunker busters out of 238. And 235 is a little more radioactive, but it's what we need for fuel. Because I don't know why, when you get a PhD, you can explain it to me. 236 is not possible on Earth. 235 is, 238 is, but 236 goes and breaks. 237 likewise does not hold up. By the way, 237 lasts a lot longer than 236. 236 is like spontaneous breakup. So look, here's why we use 235. This is where you need to start taking notes. I'll stop 3 different ways.
Wait, then why is that 236 in there?
You'll see. You see how it's surrounded by little rays? Okay, everybody, here we go. The nuclear reaction. This is the most common nuclear reaction on Earth. You start with the 235. That's the fuel. You make it a little bit heavier by adding a neutron, and that makes it 235 plus 1 is 236. You see how it has an asterisk? Asterisk means unstable. That will not hold together. It's like, wow, that bus looks really full. Can I get on? And it goes, and it breaks. When it breaks, it gives off a lot of energy, like a lot of energy. Nuclear power is called fission because the energy comes from splitting an atom, like this, where that one breaks up into little stuff. I will continue my explanation, but are there any questions what I've said so far? Yes. The 236 is the big atom that cannot hold together on our planet. So we make it because we know it's going to break. And in the process of breaking, we get energy out of it. So you find something that spits off neutrons, like voodoo magic and leprechauns. You rub it on your 235, and it makes it heavier, and by becoming heavier, we wanted it to break. That's why we built it, so it would split and give off the energy we need to harness. Yes?
Couldn't we do that with other elements that aren't quite as toxic?
They would become just as toxic on the way to getting big enough to break up, but we'd have to be adding protons and stuff to make them unstable. You see, we want the nucleus to split. If you take something lighter and you start throwing neutrons at it, you'll make heavier and heavier isotopes until they can't hold the neutrons, and then you just make something radioactive that will spit off neutrons, and who cares? There's no energy there. You understand what I'm saying? By adding radioactive components, it's just going to spit off those components, but it won't split. The secret of uranium is it's right at that Goldilocks moment, where it's not quite too big to exist on Earth, and it's not quite so small that it remains stable. By adding one neutron, it falls apart, and that's the goal, splitting the atom to get the energy out.
And also, like, how come it's only spitting out, like, neutrons? Like, I know there's, like, alpha, beta, and gamma rays that get sent off. Like, how are there no, like, electrons? Does it depend on the amount of protons and neutrons in the atom?
In this reaction, there are other radioactivities that I'm not featuring here. We can just call them energy for you.
Okay. But there are, like, electrons and...
It would make sense. It would follow the reason. Probably some hydrogen ions, yeah. Anybody else? Yes?
Is the reason we use uranium because it has a really high melting point? Like, so it can be hot, or?
No. The reason we use uranium is it's at that Goldilocks point, where it's just big enough to remain stable on Earth, but by making it a little bit bigger, the atom will split. That's where we get the energy. Yes?
Is radioactive waste what's left over from the U-236?
I promise I'll get there, but not yet. Yes, and I'll get there. What else? Nobody else? So look, 235 plus neutron makes 236. That goes bang. When it goes bang, you get a lot of energy out. We'll come back to that. But in addition, it breaks up into little pieces. On average, they are these. I'll describe it in a minute, but first a concept. Imagine each of you has built the same Lego castle. I give you the box, you take it out of the box, you dump out the bags, you follow the instructions, and each of you builds the exact same Lego castle. And then, on the count of 3, you all push it off your desk at the exact same time. I don't know if you guys have ever built Lego castles, but for me, there are some pieces that never stay on. Like the flagpole. Those flagpoles, they have a lot of leverage, and just one little button, they never stay on. You guys notice that? Yeah. And if you ever build a Lego castle, there might be certain weaknesses. Like hers might break up into 5 pieces, and his might break up into 2. His might actually hold together, and hers breaks up into 3 pieces. But his will probably break up into 2, and his will probably, and on average it'll probably be 2, because there's a certain weakness. Like at the top of the drawbridge, where there's just a couple of Legos touching it together, it'll probably break there, right? And if it breaks there, then, you know, it'll have the same average number of pieces. It'll always break off the really weakly attached parts, like the flagpoles. Those are always going to fall off. Hers might be a total of 17 little pieces and 4 big chunks. And hers might just get lucky and fall and land right and no pieces fall off. It's possible. But on average, if you all build the same castle, we will find an average number of parts left over. Do we agree? The average? That average will be defined by a couple structural weaknesses of your castle, right? Like the flags don't usually hold on and the drawbridge usually breaks. Okay, watch. When you break uranium-236, on average, you get a couple of little pieces, like some loose neutrons. That's the most common type of radiation, Audrey. Is the loose neutrons. And on average, the nucleus will break into 2 very heavy atoms. The average is tin-131 and molybdenum-103. That says SN-131 and MO-103. You'll have to write that down. There are many radioactive decay products. This is called radioactive waste. And please look up, because I got to tell you about those waste products. These are called radioactive decay products as a general term. These are quote-unquote hot, which means they will continue to decay. In other words, they're going to give off their spare parts. In other words, that's what radioactive means. these will give off many neutrons because they're very heavy. They have a lot of extra baggage. I got to double check on some things. First of all, let me say this again, and if there's any of this that's confusing you, don't give up. Write it down. We can talk about it. Don't lose the details. You'll need all these details. If you fail to put them on your paper, that's on you. You can watch the video, but keep up with the details. We take 235, throw a neutron, make it 236, which is inherently unstable. It goes, and when it blows up, you take some energy out, some little parts, and on average, a couple of big parts. Those big parts have a lot of extra neutrons. Those are really radioactive. Now, I'd like to check with you about one detail. Remember I told you a school bus can hold a whole bunch of extra parts, but like a Volkswagen Beetle can only hold a couple of extra pieces of luggage? Does that make sense to everybody, my analogy? If you take 40 extra bits of luggage and you pack all those people into 2 passenger vans, the passenger van probably cannot take 20 bits of extra luggage per van, right? Because this is a van and there's already people inside. You know what I'm saying? So the point is, uranium could hold a lot of extra neutrons. It was a little radioactive, but it could hold them. These guys cannot hold those neutrons. The radioactive waste is more radioactive than the fuel was in the first place. Because you've taken a big atom that can hold extra parts and split it into small atoms that cannot handle all those extra parts. So they will decay and fall off, and that's what radioactivity is. The decay products are more radioactive than the fuel was in the first place. Smaller atoms are less capable of holding all those extra parts. Robin. Good.
Then how come it can hold 3 more extra neutrons? Or do they not split up the atom?
Uranium, you mean?
Because it says uranium 2,
Yeah. So I don't know why. PhD, when somebody gets a PhD around here, they'll explain it to me. The 235 is relatively stable. 238 is pretty stable, but 236 is impossible. Something about the geometry. It's like the lopsidedness, and then it...
Can you make 238 from 235?
Theoretically, I think it's possible if you attach 3 neutrons at once, except the challenge is you can't deliver 3 at once. Because when one of them touches before the other 2, you've got 236, and that'll blow. So theoretically, if you could add 3 simultaneously, it would hold together just fine. Because 235 is pretty stable, and 238 is pretty stable. 236 is impossible, and that's between the 2. So usually, when you try to add 3, the first one hits and it blows up before the other 2 stick.
So does the chain reaction just keep on happening until the neutrons are out? Like 118 times or whatever?
It'll take a while to get to that answer.
Okay.
Yes?
Uranium splits into tin and what other?
On average, it's tin and molybdenum. But technically, it can be a bunch of other stuff. That's just the average. You know, like a Lego castle might break into 2 pieces on average, but each of those pieces, if you look at it 1,000 times, would be a little different. So those are just the average. Yes?
Can we synthetically change the number of protons in atoms or no?
That's called alchemy.
Is the energy in the neutrons still, like, in your analogy, the little?
And yes, but it takes about 1 billion units of energy to make 1 atom of gold. Sorry.
The little parts that come off of the castle when you...
Those are the neutrons.
Yeah, the 2 neutrons and then the energy, is that, in your analogy, like, not the big parts that fall off the castle, the little parts, or does that not even
Big parts, little parts, the magic of chemistry. Big parts,
So, like, but that's like the
little
flag.
parts.
It's like the flag that falls off.
These are the flags, the little parts.
Okay.
The energy is just like, whoa,
Okay.
bonus. That's why we do this. Yes?
I'm not sure if you went over this already, but in the chain reaction, like the little parts are like
I did not go over the chain reaction yet. Are we ready for the chain reaction? I have an analogy before we do this. Imagine my classroom. I do a lot of this analogy. If you're paying attention and you follow the imagination thing, it'll help you out. Watch. Imagine this classroom is packed full of firecrackers.
I have a feeling it is.
I went to Tennessee and I got firecrackers, and my kids were like, "Oh my God!" And they wanted to move to Tennessee. They actually wanted to move to Alabama because we bought them as we were driving through Alabama. I was like, "Oh." So yeah, if this room was full of firecrackers, and I just throw one little spark to light one firecracker, that first firecracker will go bang, right? And that'll give off a couple of sparks, which will make a couple of other firecrackers explode, right? If each of those goes off, and each of those makes a few sparks, then a split second later, we'll have like 4 or 8 going off. Do we agree? And that'll make more sparks each. That's the chain reaction. Because everybody remember, this is one atom, but the fuel is 3%, 235. We're talking like hundreds of pounds in a nuclear reactor. So there's a lot of this stuff around. Watch. You make one of them that blows up and you get more sparks. Each of those will ignite a neighboring atom of 235, and those go bang and make more neutrons. Now we've got neutrons all over the place, and each of those will light more reactions. This is the chain reaction. Imagine, I say, here, you've got an auditorium full of firecrackers. Try to slowly roast a marshmallow by lighting them on fire. You'd have to find a way to suppress the sparks, right? Does that make sense to everybody? Am I mixing my metaphors too much, or is this working? So watch. The only control method is to trap those neutrons. And there's another problem. There's this exponential growth thing where the first neutron makes 2, and this one makes a total of 4, and those make a total of 8. That's called exponential growth, right? As the neutrons grows exponentially, so does the heat. And so does the amount of radioactive decay product, and each of those gives off neutrons too. So you get this snowball effect, where more neutrons makes more heat, and more heat encourages more reactions. So now you've got all these neutrons that are making a whole bunch of reactions, that are making a whole bunch of heat and neutrons. And so it's like, oh my God, oh my God, oh my God, and all of a sudden it goes bang! And all the uranium goes off at once. That's what we call a meltdown. It's not an explosion. It's the heat which is the problem. When a reactor melts down, there's no concussion. There's no like, it's just like, holy crap, that's really hot, and you evaporate. Yeah.
If it's so hot, how do they like, how cold is the water to contain it? Because wouldn't even like near freezing water not be able to? Or does it mix it with a chemical that makes it not freeze so it can go away?
Whichever liquid you use, you've got to keep it moving and you've got to keep it cold.
Right.
So like what happened at Fukushima is the spent fuel rods, this stuff, were sitting in a pool on like the 7th story of a tall building. And when there's an earthquake, the top of the building sways, and so what happens with the water in the pool? Splashes out. So now you've got these fuel rods out in the air. Nothing to take away their heat. Power outage, so the water stops moving. And then they start to build heat, which builds more reaction, which releases more neutrons, which builds more heat, which builds more reaction, which releases more neutrons. And then the water evaporates. And as that water evaporates, it gets extremely hot, and the roof starts to melt. And then you've got radioactive stuff in the air, and then everybody freaks out.
What? How do they control it?
They like shot water into it with like fire hoses, and they tried to drive a helicopter over it, but it was so hot that the helicopter got diverted, so they went back to the pumping water thing. Yes?
How did the water splash out through the roof?
The roof is on the building. The roof was not in the ponds. So it makes like a hot tub with no lid in a building that has a roof. The water splashed out of the hot tub, not out of the roof of the building. That's a really good question. I don't know. To dissipate the heat, probably. Probably to dissipate the heat. You know how if you leave the lid off your jacuzzi, it gets cold at night? Any more brain busters? I don't have a lot of time to explain how the reactor works, but I can. It won't take very long. But I got to make sure that this made sense to everybody. We got all this? Nothing else you want to ask me? Because I'm here for you. Yeah. Every single thing I said. Yes.
What does it say that in the last parentheses, the small?
Right down there?
No,
Right there?
left, the back.
Yielding on average this stuff. The average. Yes.
So the plus or minus the two neutrons that we release, that creates U-235? 235.
Those will add to other 235 to push them over the edge, and then they blow up. So it doesn't create 235. It creates 236 out of 235, which causes more reaction.
The chain reaction part.
Yes.
Yeah.
So they will add to 235 to make them into 236, and that makes more reactions. The point is, once you start the reaction, like a spark in a room full of firecrackers, the outcome gives you more and more. You dig? All right, check it out, everybody. This is the most common type of nuclear reactor. You have to know how it works. That's why I'm glad you already copied the drawing. It'll be on the board tomorrow if you haven't finished your drawing. But please try to follow with me. From my arm to the right, this is every power plant ever, anywhere. All power plants have a steam, turbine, electricity for the grid, and you use cold incoming water to cool down the steam so you can reheat this stuff and get rid of the heat somewhere else. Do you guys know what happens if you take a cold can of soda and leave it on the counter while you take a hot shower in a steamy bathroom? When you come out, what has sprouted on the outside of your can of soda? Condensation. Remember, that's because the heat of the steam went into the can, so you now have hot soda. But by giving the heat here, the steam has turned into liquid on the outside. Does everybody understand that, how condensation works? The steam gives away its heat to another liquid, so it becomes a liquid itself. Does that make sense? So watch this. You bring in cold water, make it into hot water, and you fizz it into the air to make steam, or you dump it into the ocean somewhere. If you've ever seen like every cartoon ever, when they show you those cooling towers, like on The Simpsons, there's a radioactive symbol on them. And if you've ever watched The Simpsons, when they dump the water out into the river, there's a fish with 3 eyes. This is a lie. It's not radioactive. It's just warm, like temperature-wise. I would love to take a sauna in that tower. No problem. I am not afraid. It's just steam. It's not radioactive.
That's just,
Steam? It's just steam.
Let me get this straight.
Yes.
Just steam.
Yes. I'm here for you. It's steam. That's right. Look. I don't know if anybody's ever been down to San Onofre, the 2 boobs next to the coast, the power plant. The reason that this one doesn't have cooling towers is because they just pour the hot water into the ocean. No big deal. It's just hot water. It's not radioactive. It's just hot water.
So we're all
Pretty hot.
Hold on.
Yeah, so they have to dissipate it. There's ways of, so it's kind of thermal pollution, that's true.
It's radioactive.
So the rest of the energy and stuff is just all going straight to electricity and whatnot.
Now look, The whole point of a nuclear reactor is to make steam with this very carefully managed nuclear meltdown on the edge of happening. You got to make it hot enough for steam, but not hot enough to melt. You got to have some radioactive decay to make energy that you need, but not too much, or everything melts and then everybody dies. You are quite literally playing with fire. Allow me to explain. There is a containment structure which is meant to contain radioactivity. Steel and concrete, very sturdy. Those things are really, really sturdy. Very expensive. A lot of steel, a lot of concrete. They are meant to sustain tremendously high temperatures, earthquakes, all that stuff. The containment structures. Inside the containment structure, you have the reactor core, which is fuel rods and control rods of boron, with a liquid coolant that is pressurized water. You should be taking all these notes. It's called a pressurized water reactor because of this, water is under great pressure. You know what happens to water when you heat it up? It becomes steam. But what happens if you have water and you keep it under great pressure when you heat it up?
Steam.
No, it just gets to be really hot water because it can't expand into steam. It's under pressure. You guys know that? That's how a pressure cooker works. Like a pressure cooker on your stove, it cooks your food faster because it's much hotter than water. Because the water can't evaporate because it's a pressure cooker. So watch, I'm almost out of time. Look at this. This pressurized water is not just hot, it's very extremely hot, like hundreds and hundreds of degrees hot. So hot that when you put that pipe into cold water, it makes the steam, and that's how you get your turbine spinning. Then the condenser will take away the heat and bring you back cold water so you can make more steam. Look at this. When that primary loop has given up its heat, you've now got cold water that you'll heat up again in the core to bring it back really hot. So, a very simple way to look at this is to follow the heat from the core to the pressurized water in the first loop, to the steam generation in the second loop, to the condenser loop, and back out into the air or ocean. That's the whole thing. Remember, the control rods will soak up neutrons if you're getting too many reactions. That's called the moderator because it moderates the rate of reactions. It slows the chain. And then you've got to keep the water moving to shed the heat. That's the coolant, the water. There were some questions. I'm ready for them. Yes?
Does the steam that is released, does that have an effect on heating up the ozone?
No, and we're not worried about ozone heating. Yes?
When a radioactive, or I mean a nuclear plant gets decommissioned, how do they extract the control rods without it causing a meltdown?
They have to be shipped together. So
So they just pick up the whole thing and move it, basically.
yeah, the fuel rods have to be bundled with moderators. Carlton?
So,